Good morning, and thank you for the introduction. Apologies, Alan won't be able to join us. I messed up the time zones when I signed him up for it. I did not realize it was the middle of the night in Australia. We are from Google. Disclaimer, this is not an official Google project, so we cannot guarantee Google support going into the future. It's open source, it's on GitHub, so please come and check it out. Okay, so in one slide, we're starting with a soft core RISC-V CPU, and you're going to add your own custom function unit to extend it. And because everything's soft, it's basically a pile of RTL, and you can put it on any FPGA. And FPGA, if you don't know what it is basically programmable hardware, including a bunch of programmable random logic, embedded memory blocks, and DSP blocks, which can do multiplies quickly. And of course, programmable interconnect to hook them all together. So with these resources, you can create any circuit programmably. And we're targeting TinyML, that is inference at the edge, quantized, typically 8-bit integer quantities, very constrained resource utilization. And the key thing is we are going to specialize the ML library, the kernels, and the CPU plus your extensions for your particular model. So it's not just domain-specific specialization, like, okay, we're going to speed up TensorFlow. We're speeding up your particular model by using custom instructions. And the playground aspect is we're going to try to make it really easy to get started and really easy to iterate, so you can explore a lot of different directions. Very low overhead, you can turn the crank very quickly. It's fully open source, not tied to any particular FPGA vendor. And we really have developed this with the expectation that you have an FPGA board sitting right there, and you are building your new processor and you're putting your ML software right on the FPGA board right there next to your laptop. You don't have to have it, but that's what we tuned it for. Okay, so how could you use it? You could actually deploy this as a solution for your edge ML in your product. And just, I mean, you might lose a little performance off the top compared to a hard solution, but one key benefit is that when you send an update to add new features or exploit new research in ML, you're sending not just a new ML model and software, but you're actually sending a new CPU, a new processor with your new extensions every time you do an update. And because it's not tied to any particular FPGA, you have much lower risk related to single sourcing your silicon or using some other company's proprietary tool chain, because it's all open source. But again, if if you start deploying an FPGA and your design stabilizes and it looks good and your volume is ramping up, nothing's stopping you from taking that and taping out a hard silicon chip based on your RISC-V and extension design that you've developed on the FPGA. It's also a great opportunity to learn about ML, how the software and hardware work together, and how to increase performance. Because using this, you're going to be working on the metal and get your hands dirty. And finally, if you're doing research into new ML approaches, but there's no hardware that supports your new approach, this is great because you can co-design as you're doing ML research. You can build new hardware to support that. Did I mention it's open source? Okay, everything from top to bottom is open source, starting with the RISC-V ISA, going to the softcore implementation, the SoC, and on top the TensorFlow machine learning library. So the outlines, some background, then into the CFU playground and a couple examples. Okay, what exactly is a custom function unit here? Because if you've designed a coprocessor or custom function unit or accelerator, you know there's many different ways you can hook it up to the main CPU. So in our case, you can think of it as centered around an R format instruction. You get 2 operands from the register file, you do something with it, and a result comes back that goes back into the register file. We do have handshaking on both the request and reply side from the custom function unit. So that allows you to have multiple variable cycles, which allows like an iterative type of computation. And while the CFU is busy, it can refuse to accept the next instruction, or you can have it pipelined, or you can even have it kind of split phase where one instruction hands off some data to this custom function unit and tells it, okay, start doing your computation. And then the CPU goes and keeps doing its own thing. Then later it issues a different instruction to get the data from the CFU. So pretty much any type of interaction is allowed, except the CFU cannot interrupt the main CPU. There's no direct connection between the custom function unit and system memory, but the CFU can contain its own state, its own registers and memories that persist. And finally, the way we structure it is you have a single custom function unit, but we send it bits of opcode so it can implement many different custom instructions. This is what it looks like graphically. Sorry about that green box, but anyway, this is a very abstract RISC pipeline looking at just the data flow for an R format instructions. So you get the operand fields from the instruction to look up the do two reads from the register file, feed those to the ALU, do something based on the opcodes, and write it back to the register file. But also there's a bypass network so that it's forwarded to the immediately following instruction if it consumes that data. So here's where the CFU fits in. The key things are that it's fully integrated with the bypass network. So it is just as tightly coupled, and there's no extra delay getting to and from the custom function unit. Even though it's kind of drawn with these blocks between the CFU and the main pipeline, in truth, when you flatten the design for FPGA synthesis, place, and route, it's all flattened. So really the CFU is pulled right into the main processor pipeline. I mentioned the handshaking, so that's these valid ready signals. And that needs to tie into the pipeline control because the CFU can stall the main CFU pipeline. So how it works is when you get an instruction and the opcode is the custom 0 opcode, those 7 bits, then the pipeline knows that, oh, this is for the CFU. It raises the valid signal to tell the CFU that this is for you. It sends the funct7 and funct3 fields, that's like a sub opcode to tell the CFU what to do. It sends the 2 operands from the register file, and then later at some point when the CFU says it's done, it gets the result back, feeds it back to the bypass network and back to the register file. So why a CFU approach? Well, especially in ML, there's a lot of time spent in a very small amount of code. So we're hoping that by jumping on just the hotspots, that you can do a small amount of hardware level design to exploit the bit level configurability of the FPGA and leave all the rest of it in software running on the soft core CPU. But one thing that we've really discovered that we like is this iterative approach. You can start with a fairly simple instruction, probably something that you cherry picked from one of the RISC-V ISA extensions from bitmanip or pack data, and say, okay, that's working. And then you take another step and your custom function unit keeps growing with more instructions, maybe more state. And before you know it, you have almost a full-blown accelerator. Okay, this is what it looks like from software. Well, you know, it's basically an R format instructions in assembly. And by using GCC inline ASM directives, you can freely mix it with your C, C++ code. This is what our macro looks like. The sub opcodes must be compile time constants, but the other 2 operands, these are the 32-bit operands you give to the CFU. Those can just be C variables. Even a small C expression will fit in here. So this is kind of important for a quick iteration. When you add a new instruction, you don't need to recompile anything with the bin utils or the assembler or the C compiler. It just works right out of the box because the macro directly generates the 32-bit instruction encoding that you need. Okay, to go back here. Now, to make it a little more readable, you might want to do another pound define where you define each of your new custom instructions with a more meaningful name like Mac or init or read back from CFU or something like that. And again, it mixes completely freely with C code with no overhead at all. So here we have a little sequence doing a load from a pointer, then 2 custom instructions and a store back to memory. And when that's compiled and disassembled, it maps to exactly 4 assembly instructions. Now, the obj dump, because we don't touch it, it doesn't understand our new custom function unit instructions. So we wrote a little script to do some post-processing so that it's more readable in terms of the source and destination registers. Okay, TensorFlow Lite for microcontrollers. Now, if you're familiar with TensorFlow, you know that it's huge. Not very appropriate for running on your thermostat or your other IoT device. So at Google, we've developed TensorFlow Lite for microcontrollers. It's a very streamlined library, very small runtime. It fits in tens or hundreds of kilobytes, compatible with bare metal, no Linux, no virtual memory, no malloc. The flow would be you train your model in TensorFlow, but then you export it to TensorFlow Lite. And usually during this step, you're also doing quantization to get it from floating point down to 8-bit integer quantized data. The model contains a graph of the operators, the tensor shapes, and the constants, the weights and the biases. And the model is brought in at compile time, so it's actually embedded in the binary executable. The interpreter is very simple. It walks over the graph, looks at what the op type is, dispatches to a kernel. Now the kernel is the code that actually performs that TensorFlow operation, convolution, depthwise convolution, typically a very deep loop nest that iterates over the different dimensions of the input tensors and output tensor. There's no JIT. Again, it's a very lightweight runtime. The kernels are handwritten. There's a reference fallback version, but the way optimization is, we ask each vendor that wants to use TF Lite for microcontrollers to please optimize this kernel for your architecture. So Tensilica provided a convolution kernel that's optimized for the extensa, and ARM provided one for CM/sys/NN. So this is where we're going to plug in our hand-optimized kernel that will exploit our new custom instructions that we're going to add to RISC-V. So if you're hoping for an ML compiler talk, I'm sorry to disappoint. In CFU Playground, you are the ML compiler. This is what it looks like graphically. So we have the TensorFlow model over here. Every instance of, say, a convolution maps to the same kernel, which is usually points to a more generic one, but it can detect, say, there's something special about this, and I'm going to write a specialized version. So in this case, we see that the filter shape is 1 by 1, and that lets you eliminate a couple of those loop nests that I talked about. So it's a much simpler routine, and you can dispatch to this specialized one, and we're going to exploit that. Okay, so let's go over the CFU Playground. My goal here is just to show you that it's easy to get started, both in terms of the gateware and in terms of the software. So I guess you have the picture in your head that I'm adding a custom function unit that you're going to design, and we're going to add it to a soft-core CPU, which you don't have to design, which is provided. But even that sitting in the middle of an FPGA is not very useful. I mean, you can access it using JTAG, but it's not very useful. So you need to build this SoC around it to hook it to the outside world. And actually, you don't need to build it. We take care of that, and we use Litex, which is MeGen, MeSoc-based core SoC builder. What's MeGen? MeGen is a toolbox to create FPGA designs in Python. You don't really need to know this, but it's Python under the covers. Litex is really great. It does a lot of the dirty work for you. It has a board library, so you don't have to worry about which pins of your FPGA map to which LEDs or the UART or the DDR memory or other IOs. LiteX already knows all that. It encapsulates how to call the vendor tools. You don't need, it actually handles everything up to and including putting the bitstream on the FPGA board. And by abstracting away from the board in this way, it makes it easy for us to target different boards. Graphically, this is what it looks like. Everything down here in the blue is handled by LiteX. We use this great RISC-V soft core, VexRISC, and the only thing you need to provide is this little bit of CFU, and everything else gets built and all the infrastructure for putting it on the board. So where it hooks in is as Verilog. However, you can generate that Verilog from your preferred design system. It could. We've been using NMyGen, but there's also MyGen, Spinal HDL, which is what VexRISC is written in, Chisel. I never know how to pronounce this, if it's Silice or Silice, but anyway, as long as you can generate Verilog, we can hook it in. Okay, what does the software look like? For doing our development, we found it useful to just put everything into one big blob. And it's menu-driven interactive. So it includes the TensorFlow models that you're investigating. For you to do profiling, it has unit tests, it has your project-specific custom function unit tests. It has some micro benchmarks, so you can check out your board, see how quickly you can do sequential memory access, strided memory access, so you can kind of get a baseline of how fast you should be going. But the thing is, it's all provided, so it'll work out of the box, and then as you build up your project, you can extend it and override parts of it. So we have the TensorFlow library, specifically just the part needed for TensorFlow Lite Micro, not the entire TensorFlow library. The stuff we've written, the common software source, and then in your project, you provide some specific software sources, and in particular, you modify the kernels. This is where your project-specific kernels get dumped in, and with the overlay mechanism, the way it works is we first copy this into the build directory, and then if there's any paths from your project that match, that gets laid on top of the original version. And this is how the kernel that you wrote will override the default one from TensorFlow. So building is really this straightforward. After you've cloned and done some pretty basic setup, you CD into your selected project. Just by being in that directory, it knows that that's the project you're working on. So make prog, that builds the gateware using your CFU and puts the bitstream on the FPGA board. So I've already done that. And then you can build the software, and then make load puts that RISC-V executable into the memory on the FPGA board, tells it to start executing it, and connects to you via a terminal program. With my earlier difficulties of presenting, I'm not going to try to switch over to that now. So once you've cloned the playground, you would start by copying a template to make your project, and then you start modifying it. Well, actually, you would build it before you even do any modification. You might add in your TensorFlow model that you're interested in. Execute it. Without doing it, the default way it's set up is for each layer, it'll print out a cycle count. Then there's another post-processing script that will tell you the total for each operator type, how many cycles you spent in that operator type, so you know where to attack for optimizing. We do support debugging because, as you might imagine, as you're designing both your new hardware and the new software to use it, occasionally you may introduce a bug. So we provide it at many levels at ISA simulation. We really like Renode. I think it actually uses Qimo under the cover, but it's like Qimo on steroids because it can also emulate all the other peripherals on your FPGA board. Verilator is useful when you really need to get down into some timing issues, especially if there's some issues with the handshake between the CPU and the CFU. Verilator will give you that and give you waveforms to stare at. And we're really excited about down here at the bottom about this co-stimulation where you can simulate the CPU in an ISA simulator using Renode and couple it with Verilator simulation of your custom function unit so that you're actually using your Verilog. So you're really testing your design. Okay, examples. In the first model that we looked at, we saw the convolution is taking up 3/4 of the execution time. So, okay, let's dive into the kernel. We have this loop nest iterating over the different dimensions. What we would really do first is stick in some printfs and look at these parameters, and we discover, oh, our batch size is always 1. So we'll optimize, we'll just assume our batch size is 1. And maybe there's some other things, and you can specialize this loop nest. But the fun part is where we get to add our new custom instruction. So let's look at this in the very heart of the innermost loop, there is this multiply accumulate. And it has a little twist. You add this offset before you do the multiply. So you might be scratching your head, okay, well, but there's actually 4 operands here. There's the 3 on the right-hand side, and also you need the old value of accumulate because you're going to be adding into that. So you're right, this doesn't map exactly to a single custom instruction, but we notice that input offset is loop invariant. So that means it's constant for the duration of the loop. So what we can do is we can move it into the custom function unit and store it there. And similarly with the accumulator, we can do that accumulation within the CFU. So we don't need to keep moving it back and forth with each time we do this multiply accumulate custom instruction. This is an abstract view of our RTL. So it has the 2 operands along with the function ID, which is like the sub opcode, and has a little bit of decoding. So there's going to be an initialization instruction that will load one of the operands into the input offset, and then it's just going to stay there until it's changed. And it will also zero out the accumulator. And then the main multiply accumulate custom instruction will just need to be given a new filter val and a new input val each time you execute it. And then at the end, you can pull out your final accumulation. And this is how the modified code looks like. You know, I didn't realize till after I made this slide that we could actually combine these two, but actually it's a little bit different because input offset is really constant for the entire routine. So you would just move that in once, but then you actually have to zero the accumulator multiple times each time you enter this inner loop nest. So we have these new custom instructions for moving input offset into the CFU, here for zeroing the accumulator, and then in the heart of the innermost loop, we have this, I guess, third custom instruction, which moves the filter and input values in, does the operation, and finally, at the conclusion of this loop nest, we retrieve the accumulated value and continue on with that. Okay, so that's our starting point. Like I said, the first step is relatively easy, but then you realize, well, wait, these are 8-bit values. Why am I pulling an 8-bit value out of memory one at a time, putting it in a 32-bit register, moving that into my custom function unit? Why don't I just pull the entire 32 bits of 4 values and just hand that directly to the custom function unit? The custom function unit can then unpack the values, do these operations in parallel. So this is the stuff FPGAs are really great at. Add the 4 partial sums, add the 4 products into our accumulation every cycle. So boom, we have another 4 times speed up. And then you think, well, why am I moving the filter weights? Why don't I just store them in the custom function unit? And then you keep going through a number of steps. You eventually add a sequencer for doing a full matrix vector computation, move the post-processing of the accumulator, that is the activation function and the rescaling for quantization. And then finally you get something that looks like this. So while you have your sequencer is grinding away at one chunk, you're streaming in the input values for the next chunk by double buffering. And at the same time, you're streaming out the value that you computed the last time. So my collaborator, Alan, wrote this, did this as an exercise. So this was our starting point. This is why we looked at convolution, the one-by-one case, because it dominated the execution time. So starting at over 500 million cycles. And this is this iterative sequence of development. So the titles down here are the actual comments in the Git commits. So over time, we see it, we finally get to a 5 times speedup. So this is a factor speedup, not a percent speedup. And then pretty soon you hit 20, 40, almost 60 times speedup on this one operator. So we've done great shrinking that runtime down to practically 0. But due to Amdahl's law, the overall speedup was only less than 3x speedup. So let's go back, profile again. So yeah, we've shrunk this down to insignificant compared to the other ones. So now we have a couple more that we need to tackle. And then going back to this graph, looking at the bars, these are the resource usages on this FPGA. Starting on the left side, that is our baseline for just the CPU. The CPU actually uses a good share of the block memories for its caches. And so we were a little worried, but we could see that even with this very large performance increase, we didn't really increase our resource utilization by a huge amount. Although we are using some block memories, and if we need to accelerate 2 or 3 more ops, like we saw, then we might need to start getting tricky about reusing these block memories between the different operators, because there's only one of them active at a time. And that's where we are right now in this project, which we're using CFU Playground for. Okay, to wrap up, it's open source. So if you're interested, please come and join us. And looking for users and eventually contributors, send us issues for how the documentation can be improved. It's very useful. And currently things are actually moving around because we're upstreaming some stuff into Litex and VexRISC. So it is very alpha, so be prepared for that. We're kind of thinking about what the next directions we're going to go in. We definitely want to add tiny ML perf benchmarks, just so you get them all right off the bat, because these are all very intriguing, and we'll learn a lot by tackling different types of models. Like, as you can kind of tell, we've been looking at image processing models. We really want to get into speech type of models. Okay, and then finally, of course, the CPU does become the bottleneck. So it's like, there's this constant pressure. It's like, why can't we have a backdoor to memory from the custom function unit? Okay, so we're thinking about that. Oh, and I need to give a plug to the RISC-V soft CPU and CFU task group. So what I've done here is really the simple case. Embedded, there's only one thread, no protection issues, no multiprocessing issues, no virtual memory issues. How does this look when we do get to this complicated situation? And that's what they're tackling in this task group. When you exchange CFUs with others, what kind of metadata do you need? How can you compose a system with multiple CFUs? Like, what if they are both using the same opcodes? How do you remap the opcodes? If the OS has to preempt a process, how does it deal with the state in the custom function unit? All these questions are the tough questions they're tackling here. So send me an email. I can hook you up and join us for this task. Acknowledgements, there's many others at Google besides myself and Alan. And also the TensorFlow Lite micro team have been great collaborators. Task group I just mentioned. Ant Micro has done a lot of work on the CFU Playground, plus a lot of the supporting tools, Litex and Renode. And as an open source project, we rely on all the other great open source projects. So thank you, the entire open source community. So I hope you're excited about this opportunity that you can be the architect. I mean, you might not be the best architect in the world, but you might be the best architect for your project, and we let you do that. Thank you.